So in this report, after we have run all the reconciliation and we selected all the options and we made sure that our analysis looks okay, then we can come here and now we can start learning more about this water, okay? And I was saying that one of our favorite tables today and the next class will be the pre and post scaling tendencies. And I will spend a little bit of time explaining this. What do we mean by pre and post scaling tendencies in the software? And so what I'm going to do is I'm going to show you this slide. And you'll see that, again, we have the pre and post scaling tendency. But what is the definition of a scaling tendency? Okay, so scaling tendency is calculated as the ratio of the ion activity product divided by the solubility constant KSP. You can also call this as saturation ratio, okay? Because you compare the concentration of the ions in solution to the concentration of the ions when in equilibrium, okay? So whenever the saturation ratio or the scaling tendency value is less than 1, that means that we have the liquid the ions are under subsaturation, right? And we are not expected to see any solid formation. If we have a saturation ratio equal to 1, that means that we will start seeing the formation of a small crystal that it will be in it. It will indicate basically that our water is saturated. Okay, and if we add more ions, then immediately we will precipitate solids out. So this is an equilibrium condition. Okay, saturation equal to 1, and then if we have our saturation ratio above 1, that indicates supersaturation, and for sure we will have or see precipitation of solids at the bottom of a beaker, for example. So that is what we mean about for scaling tendencies. Now, what do we mean by pre-scaling tendency and post-scaling tendency? So pre-scaling tendency, the pre-scaling tendency value is the value calculated before any solids or minerals precipitate out. So imagine you have salt, like sodium chloride, salt table, the salt that you have on your table. You put it in a beaker or in a glass, put it in the water and start mixing it. Okay, mix it very like at time 0, you just start mixing it, and at time equal to 0, or at the first time you start mixing, everything is in solution. Okay, everything is in solution, nothing is precipitating out, and before anything precipitates out, the software calculates these pre-scaling tendency values. So it accounts for all the possible ions being dissolved in solution. Okay, so this is another example of these pre-scaling tendency values where they are useful is when you have a water analysis and you assume that they have been acidified or they have been digested in acid, and that means that this acidification, this digestion is making sure that everything remains in solution, so then you can go and do the respective ICP analysis. Okay, so there is where you will use these pre-scaling tendency values. Now, there is the other scenario, which is the post-scaling tendency value. And this is when after time, or time is going to infinite, a long time has passed, you have reached an equilibrium condition, you have left that salt that you put in your beaker precipitate out, and then you start seeing a solid in the bottom, okay? That solid now will be in equilibrium with the liquid or with the solution, but it has taken some of those ions to form the solid. So you now have less availability of ions in solution. So the post-scaling tendency value is going to be different than the pre-scaling tendency value because now you have less availability of the ions that you had before, because you form now this solid. So if you have a pre-scaling tendency value that is above 1, and if you then wait a long period of time, then you'll know that that solid has precipitated out, and now your post-scaling tendency value is going to be less than 1. Okay, because you have precipitated your solid. So I hope that that's clear. You can ask me more questions about this, but I try to make my best to explain this in the software is giving you this information in this table. You also see that we are not only giving you the pre-scaling value and the post-scaling value, but we are also giving you a pre-scaling index and a post-scaling index. The reason why we also provide this is because the scaling index is another way that the industry also measures or quantifies the scaling risk. And the scaling index is simply the logarithm 10 value of the scaling tendency. So it's going to be the same. So if the scaling index is less than 1, then it means it's a subsaturated solution. If you see a scaling index of 0, means saturation, and if it's above 1, indicates supersaturation. So if we go back to the software and analyze the pre-scaling tendencies now, I am going to use the pre-scaling tendency values as my saturation ratios for all the class. So I will always refer to, I'm always looking for values that are close to 1 or above 1. So when I am seeing these specific values here, I see that the pre-scaling results for barite are above 1, that's 7.67. I see calcite being 6.05. And I also see another value, let me see, this strontianite mineral also being supersaturated. And the software has identified that for us as well. It says the brine is supersaturated with 3 solids. And it's telling you in this calculation output that those are the solids that are that could potentially precipitate out. Again, this is the pre-scaling value. So if you allow enough time for this to precipitate, then these pre-scaling tendency values will be different. Okay, what else should I show you about this table? I think that is it. That's enough information for the brine at the moment. We need to learn how to use some
Anna?
Yes?
It's just that the post-scaling values for those 3 scale types are the same number.
Yeah, and that is a good question. Let me go back. So in the design table, when we go to the reconcile, in this specific case, so like I said before, we assume that everything is in solution, right? This was a digested sample and everything remain in solution, and nothing, you don't see solids. But let's say you saw solids in your beaker, okay? So you can tell the software, okay, let those solids precipitate out. You can either go here to the option allow solids to form, or you could go here to the solid tab or the solid button and turn it on. So what this is telling you is that now include the solid phase for the calculation. Okay, so we can recalculate, and this is just for demonstration purposes. Can recalculate, and then we can go to the report. Let's see until this calculates, because now we are including. So the software is saying, yes, effectively solids were formed. And in here, you'll see a pre-scaling tendency. It did not change because this is a time 0. And because we told the software calculate or precipitate those solids, now you see that the post-scaling tendency values are 1. But I want you to notice something. Let me see if I can show you what happened. So notice that before everything precipitated out, you had a pre-scaling tendency value of 0.016. Now, because you precipitated solids, you remove some of that calcite from solution. So now that post-scaling tendency is much less than the original that was calculated at time 0, right? Same for strontianite, probably. Yeah. You also remove some calcium, or not calcium, carbonate ions from solution. So now your post-scaling tendency is less than the original that was calculated. And you'll notice that the ones that only 2 solids precipitated out, barite and calcite. Before we allow solids to precipitate, the software was saying you have 3 solids that could potentially form, and one of them was strontianite. Again, you remove some carbonate ions from solution, so now you don't have available those carbonates anymore, so they actually don't form because you don't have more availability for that precipitation reaction to occur. Okay. For my calculations, I will leave everything. I will not precipitate the solids. I want to account for all the ions in solution to quantify the risk for scaling. So that's the reason why every time that you add brine analysis, you will always notice that the solid phase is off, because we want to keep all of those solids in solution so that we can keep them all in the calculations to quantify the risk of scaling. So what I'm going to do,
Can I ask a question about this? Because how can you, if the thermodynamics predicts that these solids are going to form, how are you going to force them to stay in the solution artificially if they're going to form throughout the process?
I am going to let them, I'm not going to allow the solid phase to be part of the calculation. And again, you could have 2 scenarios. You can have the worst case scenario, which accounts for all of those ions dissolved. And you could have another scenario where you allow them to precipitate and see how much your calculations change. But when we do this type of calculations, we like to account first for the maximum risk. So the way of doing that is just to force those solids, or not those solids, is to not let that solid phase to precipitate out by not selecting the solid phase. Again, you can always have an Olympus brine solids on and the other one solids off, and see how much it changes your scaling risk. The thing is that, at least with this specific analysis, I'm assuming that the sample is being digested because it went through an ICP, right? So they must be all in solution. So that's why I'm not accounting for the solids. And that's the solution that I will use for the example. But again, you can always create another one where you precipitate the solids and do the calculations and see how much it varies. You have that option as well. That will be one that accounts for the minimum scaling risk. I will say it that way. Okay, I hope that that's clear. But the software that allows you to not to force those solids to stay in solution. Not solids, the ions to stay in solution. Okay,